So question 4 is a polarity question explaining why SO2 is a polar molecule, whereas SO3 is not. Okay, so let's try to draw out the Lewis structures of both SO2 and SO3. Go down a bit. Okay, so let's find out how many total valence of electrons SO2 has. So SO2 contains a sulfur that has 6 valence electrons and 2 oxygen atoms that also have 6 valence electrons. So if we add it up, we have a total number of 18 valence electrons in SO2. So now if we draw out our Lewis structure, sulfur will be our central atom, and I'll just draw 2 single bonds to oxygen. And these oxygens may have a double bond. And then I'll just show the 2 pairs of lone pairs on each of my oxygen atoms. So now let's count out how many atoms I've drawn so far. Each bond contains 2 electrons, and we have 4 bonds, so that's 8. And then each oxygen has 4 valence electrons, so that's also 8, so we have 16. So I just need to put 2 more electrons on my central sulfur atom. So now let's analyze the shape of this molecule. So the central sulfur atom contains 1 lone pair, and it contains 2 bonded atoms. If we were to look up the molecular shape of this molecule, we can use the Vesper table and find out that when you have 1 lone pair and 2 bonded atoms, you have a bent molecular shape. So I'm just going to say bent. And what we also need to calculate is the electronegativity difference between a sulfur atom and oxygen. So electronegativity difference is a big aspect of how one can find out whether or not a bond is polar or not polar. So let's look at the electronegativity difference. So sulfur has an electronegativity of 2.5 and oxygen's is 3.5. So let's put 3.5 minus 2.5. So the electronegativity difference is 1. And the reason why I calculated the electronegativity difference is because when we have a polar bond, then your electronegativity difference is greater than 0.4, but less than 1.69. So what this tells us is that because the difference in electronegativity between sulfur and oxygen is 1, then that means there's going to be dipole moments pointing towards the direction of the oxygens. Kind of like that. So we have a net dipole moment in the molecule going this way, meaning we have partially negative charges and a partially positive charge where the sulfur is. So notice that these dipole moments aren't able to cancel each other out, and the reason why is because of the bent shape in the molecule. So this means that SO2 is polar, and I'll say that dipole moments don't cancel. Okay, so now that we did SO2, let's look at SO3. Again, we're going to find the total number of valence electrons of SO3. Sulfur has 6, and this time oxygen has 3. So we have a total number of 24 valence electrons. So now let's draw sulfur as our central atom, and then the 3 oxygens bonded to the sulfur. And I'm also going to draw in double bonds. And all of the lone pairs. And now let's calculate how many electrons I've drawn so far. So each bond has 2 bonding electrons. There are 3 bonds. Well, 6 bonds actually. So that's 12. And we have 4 lone pairs on each oxygen. So that gives us 24 electrons in total. So already we don't need to add any more lone pairs on the sulfur. We already have our 24 electron count in this structure. So let's find out its molecular shape again. So this time sulfur has 0 lone pairs. And we have 3 bonded atoms. So now let's look at our Vesper table to find out what kind of shape it has. So when we have 0 lone pairs and 3 bonded atoms, this means we have a trigonal planar molecular shape. So therefore, trigonal planar. So we don't need to calculate the difference in electronegativity since we already did that previously, but I'll just recall that the difference in electronegativity is 1. So again, you're going to see the same dipole moments going towards the direction of the oxygens. But now you'll see this time there's no more lone pair on the sulfur, so all of these dipole moments will cancel each other out. So therefore, we can say that SO3 is a nonpolar molecule. The dipole moments cancel each other out. Okay, so now let's see what the junior tutor said. SO2 is a polar molecule. Polar molecule is a molecule in which the distribution of electrons between the bonded atoms is uneven. That is, one molecule is slightly positive while the other molecule is slightly negative. To determine whether a molecule is polar, the electronegativity difference between sulfur and oxygen can be compared, which is a measure of tendency of an atom to attract electrons of a bond, and they can be seen on the periodic table elements. Well, sometimes. And from the periodic table, the electronegativity of sulfur is 2.58, while for oxygen, it's 3.5. So from this, we can see that there's an electronegativity difference between the sulfur and oxygen atoms, so that's greater than 0.4. So this causes an uneven distribution of electrons and makes sulfur dioxide a polar molecule. The Lewis structure of SO2 is shown below. Okay, so they got the same structure, and it can be seen that there's an unbonded pair of electrons on top of the sulfur. This makes SO2 to have a net dipole moment. For SO3, it is nonpolar. It has equally shared electrons between the atoms in a molecule. Not really, they still have an unequal share of electrons. It's just that they are arranged symmetrically that makes the dipole charges cancel each other out. Note that there's an electronegativity difference between sulfur and oxygen atoms. However, its net dipole moment is 0. You can see it's a symmetrical molecule that is trigonal planar. And that is why SO2 is polar, whereas SO3 is nonpolar. Okay, so this solution is correct.